Today we're going to be talking about graphing linear equations from slope-intercept form, which is probably the first form that you ever encountered when graphing linear equations. That's anything in the form of y equals the slope times x plus the y-coordinate of the y-intercept. So in particular, we tend to call the slope m and we tend to call the y-intercept b. That's just by convention. There's no particular reason to abbreviate that way. But whatever number is attached to the x, that is your rate of change because it's the number being multiplied by x. So that is your slope versus the number that's by himself is always your y-intercept. Recall that you always could rederive the y-intercept by plugging in x is 0, and you would find in any type of equation, well, if I plug in x is 0, that means the number attached to the x times x. Anything times 0 is just 0, and you would just be left with exactly that y-intercept there. So that's always something to keep in mind. If you can get the slope and the y-intercept, what you want to do is start at the y-intercept and then move according to your slope, remembering that slope tells you rise over run. And if he's a positive slope, that means you either want to move up and right or alternatively down and left, since down and left would be a negative over a negative, which simplifies to a positive. Versus if he is a negative slope, you have two options. You would either move up and then left to indicate positive then negative, or you could move down and then right to indicate negative then positive. Either way, you want to start at your y-intercept and then move according to your slope to find a couple other points. So let's go ahead and try that with this next example. So first things first, go ahead and pause your video and see if you can identify the slope and y-intercept, and then see if you can graph the equation. Well, here our slope is the number again attached to x, so it would be 1/4, and our y-intercept is the point 0, negative 7. Notice how with the y-intercept, the negative is attached to the y-intercept because that's like plus a negative 7. Then we're going to start at our y-intercept, so start down here at the point 0, negative 7, and then move according to the slope. So one direction we can move is, let me actually do the movement with a different color than what I'm actually graphing the line with. 0, negative 7's here. So we can move up 1, right 1, 2, 3, 4 to get our next point here at 4, negative 6. Alternatively, instead of moving positive, positive, we could move negative, negative. So we could move down 1, over 1, 2, 3, 4 in the negative direction to alternatively get a point negative 4, negative 8. Either way, what we've just confirmed is at least two other points on the line. And then we want to do a quick sanity check. Does it indeed look like that's my y-intercept? And with this slope, he's looking like he's A, positive, and B, relatively shallow, since he's only rising 1 per every running 4 in terms of that rise over run, change in y over change in x. And it does look like we graphed it correctly, because if I were to go left to right on top of the line, I'd be walking uphill, so it is positive. And it does look relatively shallow, so I know I didn't graph it backwards. This is kind of recapping those steps. So you always want to start at your y-intercept, rise according to the numerator of the slope. So if the slope is a whole number like 2, keep in mind 2 is secretly 2 over 1, so you'd be rising 2, running 1. And then you want to double check that if it's uphill, it's a positive slope. If it's downhill, it's a negative slope. So if you had accidentally moved over here, you would have said, oh my gosh, that's decreasing. It's going downhill left to right on top of the line. I better flip that around and graph it the other way around. And then you want to draw the line through the points. You only technically need 2 points, but it could be a good habit to try to draw more than 2. So go ahead and pause your video and try to graph both of these equations yourself. and then we will go through how to graph those together. So for this first one, our y-intercept is at 0, -8. So that is exactly where I'm going to start, at 0, -8. And then I have two different choices. I can move up 1, 2, and then left 1, 2, 3. Or I can move down 1, 2, and then right 1, 2, 3 to give us our nice, beautiful line here. And then you can read off extra points from the graph that way as well. So our slope was -2/3, and another point, for example, would be down here at 3, -10 would be another point on this line. Next one, you want to do the same deal, so it looks like our y-intercept is at 0, 9. And then I physically can't move up 3, right 2, so I have to go 1, 2, 3, left 1, 2. And then when I connect them, I can double check. So for this positive sloped one, 3/2, it looks like I'm going uphill, which is what I want from left to right on top of the line, and my y-intercept's at 9, versus my previous negative sloped one looks like I'm going downhill left to right on top of the line, and my y-intercept is -8. So I know I did it correctly. Just like here, you wanted that y-intercept to be at 0, -7, and then going up and then right 4 for that uphill behavior for a positive slope. You can also use this information to write the equation given a graph. So we just went over several examples of how you would plot an equation, a line given the equation. Now we want to maybe work the other way around. So you want to identify the y-intercept, and hopefully that's clear. In that case, you can just plug directly into y equals mx plus b. If that's not clear, you might have to solve for b later. But at minimum, what you can find is some 2 clear points to plug in for your slope, and then use the slope and intercept to write the equation, and then maybe solve for b. So let's just, before I kind of dive into the examples that I've previously curated, let's just look at an example. So let's say you had the points given 1, 2, and then let's say 2, 5. One of those is not the y-intercept. So let's say those were the only 2 points that you could tell by looking at your graph. You had a nice, beautiful graph that had a point at 1, 2, and then 2, 5, and those are the only points you could clearly tell. So great, you know from the previous section how to find your slope. So you're going to label one of these x1, y1, the other one x2, y2. And then you'll plug in 5 minus 2 over 2 minus 1 is going to give you 3 over 1, which is 3. And then you would plug into your equation that your m is 3, because 3 is your slope. And then you would still have the y equals 3x plus b. You don't know b yet because you happen not to read them from your equation. If you did just read b from the graph, you would plug in b, call it a day. B being your y-intercept. Otherwise, you can plug in any point. I'm just going to pick the first one. Let me change colors here a little bit. So where you're going to replace y with the y value at that point, replace x with the x value of that point, drop down the rest of your equation, and then you can solve for b. 3 times 1 gets you 3. Subtract 3 from both sides to get you b is -1, so you must have just missed that in this case it was still a nice, beautiful integer that you just didn't quite read from your point of view on the graph, that it would be -1 there. So yeah, just something to keep in mind. So let's take a look at some more examples. So I'm going to encourage you to go ahead and pause your video and try to go ahead and find the equation for the pictured line. So from this example, you may have noticed that it actually does appear that while it's not labeled, there is a nice, beautiful y-intercept at 0, 3, which is what we're going to expect to find that y-intercept at. But let's pretend you didn't notice that, and we'll still do this kind of the longer way. First thing you should have noticed is, hey, I can find the slope. So the slope is going to be your change in y over your change in x. You want to go ahead and label one of these as your x2, y2, the other one as your x1, y1. And then you want to go ahead and plug in your change in y over your change in x. 6 minus 2 gets you 4, 2 minus a negative 6 gets you 8, and that gets you a slope of positive 1/2, which actually looking at this looks incorrect. So let's see if we can go ahead and find our mistake, because that's not what we should have gotten, right? So y2 is indeed 6, and that was correctly labeled, and that was our first point. y1 was indeed 2, and that was correctly labeled. That was our second point. See, that's exactly where we made a mistake. Our x2 was negative 6. Our x1 was 2, so we just subtracted that backwards. Negative 6 minus 2 gets us negative 8 for a final answer of negative 1/2. So always be sure to double check that there. I was moving too quickly and indeed wrote down the wrong slope there at first. But that's why you double check yourself. So we have y is equal to negative 1/2 x plus b. If we felt comfortable, we could go ahead and plug in directly that b is 3. Otherwise, we can plug in another point to confirm. I'm going to choose to plug in x2, y2. So y2 is 6, x2 is negative 6. Negative 1/2 times negative 6 is the same thing as negative 6 divided by negative 2, which gets you a positive 3. Then we're going to go ahead and subtract 3 from both sides here, so we get that b is 3, and just like we expected. So we're going to go ahead and rewrite that equation with that plugged in. You can also do some problem solving to match linear equations with their graphs. So let's go ahead and do a little bit of problem solving here. So in particular, the graph that's looking the most different here is G, because what do I expect G to be? Well, since G is a perfectly straight across line, I expect him to have a slope of 0. And to have a slope of 0 and y equals mx plus b, that means that you're plugging in for the slope 0x, and what's anything times 0, including a variable? Just 0. So you're looking for the equation that's just y equals a number, which in this case is y equals 4. So that would be your green graph. So that would be A. Then if we're looking at these graphs, one of these lines has a different sign slope than the other. Which one is that? That would be the purple line labeled as P. This guy has a negative slope, so I'm looking for an equation with a negative slope, and there is only one of those. That's the last equation here, so that is C. For the other equations, we're now really wanting to compare the slopes and compare them visually, and as well as those y-intercepts. So in particular, it looks like the blue equation here, equation B, has a positive y-intercept, and it's going to have a slope that in absolute value should be smaller than the other two. Why is that? It's less steep. So we're looking for the equation with a positive y-intercept that is less steep than the others, and that would be equation 1 here. So that would be the blue equation there is y equals x plus 2. Now for the remaining equations, which one is steeper, R or K? Well, it looks like equation R is steeper because we're going to rise more for a smaller run compared to the other equation. So it looks like R should have the larger slope. I don't know why I was trying to write in that tiny space. That should have a larger slope because it is steeper. And in particular, the equation with the larger slope that looks like he's steeper would be this equation here, y equals 5x minus 3. That would be that. which leaves us logically with the last equation to be matched. Y equals 3x minus 3 would be the one with the slightly shallower slope compared to equation R. Now, how did I know about the steepness of the slopes? Well, let's consider the slopes 2 versus 1/2, for example. For 2, we're going up 2 over 1, versus 1/2, we go up 1 over 2. So this is a slope of 1/2. This is a slope of 2. It physically looks like as the slope gets bigger, you're going to get closer and closer and closer to a perfectly vertical line. So bigger slopes in terms of absolute value, because if it was, -5, it would just, be really steep in the other way, right? Bigger slopes are closer to vertical in absolute value, while shallower slopes, such as m is 1/2, are going to be closer to a horizontal line in absolute value. That's always something visually to keep in mind. So I want you to go ahead and try this next one yourself. You're given 2 points and you want to write the equation of the line that goes through those 2 points. Well, hopefully you notice one of those 2 points actually is the y-intercept, 0, 8, and then the other point, 5, 6 here, we can kind of plot to visualize. So we're going to expect this to have a negative slope. And let's go ahead and plug in to confirm that it's going to have a negative slope. So we got x1, y1, x2, y2. So we have 8 minus 6 over 0 minus 5 gets us 2 over -5. And because that 8 is already our y-intercept, that is actually exactly equal to b. So we'd wind up with y equals -2/5 x plus 8 as our beautiful final equation. Had you actually formally plugged in to solve for b, you would have also still found that it was 8, but this is a good example that I think that would be a little bit messy to solve for. Go ahead and try this next equation yourself as well, keeping in mind that this time they did not give us the y-intercept. So here I still like to plot to sort of visualize to make sure I'm on the right track, particularly if it's been a little while since I've worked with these regularly. And here this is very, very steep, and it's not clear from the graph where my y-intercept is going to be since I plotted the points 8, -1, and then up here 9, 5, and I wrote that 5 as an 8 for some reason. So let's go ahead and find our slope. So we're going to have our x1, y1, our x2, y2. So we're going to have 5 minus -1 over 9 minus 8. 5 minus -1 is 6, 9 minus 8 is 1, and it does look like we're going up 1, 2, 3, 4, 5, 6 over 1, so it matches with our graph, and it is positive, just like we were expecting as well. So far we have y equals 6x plus b. Now we have to pick a point to plug in. I'm just going to pick the second one because I like to plug in positives when I can. So then we have 5 is equal to 6 times 9 plus b. 6 times 9 is going to get us 54. Drop that down. Then we have to subtract 54 from both sides. 5 minus 54 is going to get us -49. So then I can rewrite my final equation as y is equal to 6x minus 49. Since our y-intercept is way down here somewhere off the page. So it still exists, even if it's not physically on your page. It just might not be something that you can physically see from the graph that you've drawn. But keep in mind that these lines go off forever in both directions. That's why we have arrows on both sides, so that y-intercept does still exist, just not visible. Last but not least, let's kind of go over some special lines, which we went over very briefly. So if we have a straight horizontal line, that means that our slope is 0, which means in y equals mx plus b, we're plugging in 0 for m, and you're just left with the equation y equals b, because y is always, for all of these points, exactly equal to the value that's also the y-intercept, in this case 2. So this particular equation would be written as y equals 2 because all of those y values are equal to 2. And you could confirm that by making a table of points as well. that whatever is that common y value for everybody, that's your equation. The one that's the most different is a vertical line. So a vertical line has an undefined slope, also sometimes called no slope, but undefined would probably be the more proper way of saying it. I would actually probably argue I shouldn't even have that phrasing of no slope. I think that most mathematicians probably would not like that. But you have no slope that you can plug into y equals mx plus b, at least certainly. So it is just a perfectly straight up and down undefined line. So how do you write it? Well, you can't even plug it into y equals mx plus b. Not going to work because I can't plug in undefined for m. What do I do instead? Well, it has a similar logic to the previous one, that for all of these points, x has the same value this time. So in particular, x equals 2 would be the equation of this vertical line. If you were trying to write the equation of a vertical line through the point 7, 8, how would we do that? Go ahead and pause the video and see if you can write that vertical line and then also write the horizontal line. Well, for the vertical line, x is always going to equal the x-coordinate of that point, so it would be x equals 7. While for the horizontal line, y would always be the y-coordinate of that point, so it would be y equals 8. The biggest thing about that is that you're going to be tempted to sometimes draw it the other way around, so I would always kind of make a sketch for yourself. If we have the point 7, 8, if I have a vertical line, that means that the x never changed. So that's just always something good to keep in mind.